But we're going to see, we're going to basically see something a little different today, okay? Basically, what we've seen so far, this thing called the disk method, has been a way of taking an area and turning it into a three-dimensional shape and finding the volume of it, okay? How do we do this? What's it based off of? Based off of what? Anybody remember?
What do you mean? What do you mean what's based off?
Well, like, essentially, what are we doing with the disk method?
Calculating the area
pieces and then adding the volume.
Okay, but what pieces are we cutting it into?
We are
circles. Circles! Okay? They're circles, right? We're integrating a bunch of circles to create a 3D shape, aren't we? Whose cross-section just happens to be f of x. Okay? So what's the area of a circle?
pi squared.
Pi squared. So remember the disk-washer method is taking that pi r squared, but instead of r, we're going to use f of x, our function. Okay? Alright, and we're integrating it from wherever we're going to start the system to wherever we end it. Okay? And that basically is what the volume is equal to. Okay? Whatever that interval is. Okay? And that's this method, washer method. Same idea. It's just we have two functions. We're basically taking the area between two functions and rotating that around. Okay. Just like anything else, creating a nice perfect whole. Okay. Now, when we do these, okay, the note here that I want to stress is that this works as a revolution about the x-axis, okay? So, we're finding the volume here by taking this area and revolving it like a piece of meat on a spit around the x-axis, okay? The thing that is, as we're going to learn today, is we don't necessarily always have to do it that way. There are variations on this. Yes?
So I guess that there will always, like if there's a shape above the x-axis, everything below that shape and the x-axis will always be a hole within the shape.
Pretty much, yeah. Unless the area goes straight down to the x-axis.
Right. Okay.
Yep. Okay. So that's what the washer method is telling you. Okay. All right. But what we're going to see today is the fact that we can do this actually about other axes, if we would. It doesn't always have to be the x-axis. And we got to learn how to work with that. So there are variations on how the disk and washer method work, okay, that pop up from time to time. All right? So we're going to start off, we're going to do an example. We're going to do it under normal conditions, and then we're going to look at one of the variations, okay? So the normal one should be fairly easy, okay? Okay? This might be something like find the volume or made using the disk method for f of x equals x squared from 0 to 2. Okay? Now, I don't even need to bother to graph this because we know what it's going to be. It's just a parabola that we're spinning the zone of the parabola from 0 to 2 around the x-axis. Okay? What should the formula for that be? How would I find the volume of this great thing? The volume would be equal to what?
Integral of
0 to 2 of
Pi
x squared.
X squared dx. That's our equation for it. Okay, that's going to give us the volume of whatever this creation is. Okay, we clean this up somewhat. Bring out the pi. We square the x. It's x to the fourth dx. That's a straight up. That's a really easy antiderivative, right? So it's going to be pi times x to the fifth over 5 from 0 to 2. Okay, which is equal to pi times 2 to the fifth, which is 32, over 5 minus 0 to the 5th, so it's just 32 over 5 units cubed. Okay, so that's my volume. All right, 32/5 pi units cubed. Okay, if you will, using it the normal way. Okay, well, normal way is just spinning about the x-axis. There are variations, and we're going to see the first variation is to spin it about some other horizontal line. Okay, and so kind of basically variation 1. Okay, spin the area around a horizontal line that's not the x-axis. Okay, so let's do an example of this. Okay, basically here we're going to use the same thing. We're going to find the volume. Okay, using the disk method. For x squared from 0 to 2 spun about the line y equals -1. Okay? So instead of doing it about the x-axis, we're going to do it about a different line, in this case the line y equals -1. And we're going to see what we get here. So the very first thing I'm going to do is, I'll let you guys copy this down, but I'm going to actually draw this system out this time, okay? X squared is easy enough to know what happens, we didn't really need to draw it. But with this one here, we're going to want to have some visuals, okay? To see what's going on here, okay? Everyone understand? Yeah?
Down there, on the 32/5,
Uh-huh.
that's a unit squared.
Units cubed, that's supposed to be a 3.
What is that? Say about the y. Say
Where?
about the line.
Spun about the line y equals -1. Okay? Okay. So let's take a look at what this thing looks like. Okay? Huh? Go back.
Can you go back?
Go back briefly. There you go. Finish copying. Oh, so tired.
So we'll do the rest of the period off.
Let's take the rest of the year off.
Alright.
Actually, that's what we could do after the AP.
Good.
Take the rest of the year off. If you're a senior, that's certainly the case.
Do we have class at the AP for senior?
Yes, technically you do. Unless you're doing,
Only for this class we can.
unless you're doing one of those capstone
Senior
projects.
distinction.
Yes. If you're doing that, then as soon as you're
But that
done doing the AP,
interrupts,
you're
like,
done.
I
You're
don't
free.
understand how people are gonna do that, because that interrupts like APs.
Well, the idea is, if you're in an AP course, you still don't go to your class. So
That's the only class you need to go to.
So basically, like, if you're doing senior distinction, my class is basically an AP class. You're expected to take the AP, so you're expected to come to class still. Okay.
But like,
But let's say the class is not AP, you don't have to go.
I have like, I really doesn't have like talent. So like, I couldn't skip yearbook or yearbook. So,
Well,
I don't know.
gotta figure it out. Priorities. Okay. Priorities. All right. Everyone got this down now?
Yes, sir.
Okay. Moving on. So let's draw the picture out here. Okay. So we're going to do x squared, which is going to look like this. Here's 2. There's 0. So we're taking this area right here. So it's f of x equals x squared. And instead of spinning about the line about the x-axis, we're spinning about the line y equals -1. Okay? So, note here, my area still stops when it hits the x-axis, doesn't it? Okay? So what am I essentially doing here? I've actually created a what? A hole in the center of this thing, right? I'm taking this whole thing and I'm spinning it around, so I'm going to create this object which is going to have a hole in the center, right? In fact, this thing is going to look very much like a very strange, like, funnel. Actually, a funnel is probably exactly what this thing would look like. Okay? Yes?
Quick question. So it doesn't have to do with like this question, but as long as like the curve or the shape is touching the x-axis and we're doing it in terms of like the x-axis, we can use
This method, yeah. The washer method is only if I have an area between two curves. So
between two curves.
I'm doing this for you. Okay? But as you're actually going to see here, this is going to turn into a washer method problem.
Right.
Okay? Because what I basically have to do here is my methods that I've got, kind of my formula, work if this thing were being spun around the x-axis. We're spinning this about a different axis, but it's still a straight line. Okay? It's just a straight line that's been moved down one space. So what do you think I have to do to make this thing work then?
Make two separate.
Just push everything up one space, right?
How do you do that?
Essentially, well,
X squared plus 1.
you add 1 to everything, don't you? Okay? I essentially say, we move this thing up 1, okay? So it corresponds to the x-axis, right? We add 1 to it. That means this thing has to be moved up 1 too, right? And we add a new line here of y equals 1, because that's now the x-axis basically moving things. So essentially, we've raised everything up by 1, okay? And added a line now, y equals 1, to be the bottom of our system. So we've essentially changed this thing into a washer method problem, okay? By pushing everything up by 1 space. So, my volume then is going to be equal to the integral from 0 to 2 still of pi times x squared plus 1 squared minus 1 squared dx. Okay?
So you basically made you made it a washer method with making g of x
1.
1.
Yeah,
Or negative.
basically a straight line, in this case actually positive 1, because negative 1 moves everything down 1 space, okay? And so I want to push it back up to the x-axis, which means I have to lift everything up by 1, don't I? Okay, to make this thing work, okay? And in doing so, if I lift everything up by 1, okay, this thing basically gets lifted up by 1, that's why it becomes x squared plus 1. The x-axis gets lifted up by 1, so it becomes a line y equals 1, okay? And the line y equals negative 1 becomes the x-axis, okay? And changing this thing into a washer method problem like I've written out here, okay? So, if my line is below, I add up to get everything else. What do you think happens if my line is above? You subtract from it to pull everything back down, okay? Although, also too, at that point, there's also some orientation questions you have to ask yourself. Like, what area in question am I actually looking at, okay? We can do an example of that one second. Let's finish this one out, okay? So, that ends up being our new volume equation, okay? This right here, how would I integrate it? What do you think I have to do first?
You take the pi out.
I can take the pi out. What else do you think I have to do?
Well, you need to simplify it.
Simplify it out. Basically, I need to expand it and then clean it up some, okay? Now, luckily, x squared plus 1 squared, that's not that hard to actually square out, right? What should that come out to be? So x to the 4th
Plus 2x squared.
plus 2x squared plus 1 minus 1, right? dx, okay? And so the 1's will cancel, turning my volume becomes pi times the integral from 0 to 2 of x to the 4th plus 2x squared dx. We evaluate that. X to the 5th over 5 plus 2x cubed over 3 from 0 to 2, which gives me pi is equal pi times 32 fifths plus 16 thirds. Okay, ends up being my new volume. Units cubed. Okay, so we could figure it out. And by the way, by this point too, you would use a calculator. You wouldn't do this by hand, okay? You could pop all that easily into a calculator, okay? But notice what I did was I essentially moved everything up by 1 and created a new graph. And that's why it's important to graph out to see what happens. Everything gets moved up by 1, so my graph gets moved up by 1. The x-axis is no longer the lower boundary of my graph. It's now a new line, y equals 1, and I proceed to go from there, creating a Washer method problem. Yes?
Why couldn't you just leave it as x squared and put in -1 for g of x?
If I had done that, okay, basically put g of x in as -1, I would have x squared minus -1 squared, okay, which does not come out to be x to the 4th plus 2x squared, does it? Okay, it comes out to be a different thing altogether. And so I would end up with a different value for my volume, okay? What we basically need to make sure is that when I spin this thing around my new axis now, it's going to be a larger circular shape, okay, with a hole bored out the center of it, okay? And that's the adjustment I need to make, okay? Besides, this thing works if this thing's being spun around the x-axis only. So we got to adjust to make that happen. We can also do it about the y-axis, but we'll see that probably tomorrow. Yeah.
That 1 squared, you got it basically just from the f of b minus f of a, or...
Not quite. The 1 squared right here?
Yeah, where'd you get that
Okay.
from?
That extra 1 squared came from the fact that I've had to move everything up by 1. So, this becomes, y equals -1 becomes my new x-axis, okay? The x-axis, which is the lower boundary of the area, becomes a line y equals 1, doesn't it?
Yeah, oh, yeah.
Okay? And then x squared becomes x squared plus 1, okay? If I didn't put that 1 in there, when I spun this, I'd be finding all the area down to this line right here, and that's more than what I want.
So that 1 is basically now the distance between the new graph and the...
And yes, okay? That's where it comes from. Basically, I added 1 to everything to make sure and lifted it all up, okay? You could actually think of the Washer method, of the disk method, as being f of x squared minus 0 squared. Because 0 would be the line y equals 0, that's the x-axis, right? What happens with 0 squared?
Say 0.
Stays 0, goes away, who cares, right? And so, with the disk method, that doesn't really matter, but I can always change the disk method into a Washer method that way. By thinking of it that way, that's exactly why this thing ends up being what it is. Because the original graph here, I would say would be kind of the original one, before I changed what axis I spun around, okay, would have been, if I used the Washer method, from 0 to 2 of pi times x squared squared minus 0 squared dx, right? What's 0 squared? Nothing. It goes away. Okay? Leaving us with just the disk method there. But I moved everything up by 1, which means I have to add 1 to both my functions to make them work out. Does that make sense now?
Yeah.
Okay? And so you have to adjust accordingly. Let's look what happens to the line. So in this case, this is how things worked when my line was below the area. Okay, in this case, my new axis of revolution is below the area. Let's see what happens when it's above. By the way, you could do this when the line of the new axis runs through the area you want to spin, but we're not going to do those. We don't have to worry about those. Those don't appear on the AP. They become a lot trickier. They're not so nice as this. Okay, well let's look at the same system. Again, we're going to look at the curve y equals x squared. This is a good one to work with. Okay, from 0 to 2. Okay, there's 2. There's 0. So it's still this area, okay, that we're going to use to spin. But this time, instead of spinning it about a line that's below it, we're going to spin it about a line that's above it. In this case, y equals 5. 4, 3, 2, 1. Okay? All right.
It was the last one, y equals -1 or 1?
Y equals -1. Because y equals 1 would have gone right through the center of the area, and trust me, we don't want to play that game right now. Those are different.
Would it
Because think about it, you're spinning something around to create a solid, but half of it's below here what you want to spin, so it creates a very, it doesn't play nice.
Part of the area is like overlapping itself.
Exactly. And
so you have to like find the area of what's being overlapped and take it away.
You would have to, it's not as clear cut. It becomes a much harder problem, okay? And one that we don't need to worry about, one that we're not going to see ever, okay? This one, though, this is something you could, in theory, see, okay? The area in question is this area, and we're going to spin this around the line y equals 5, okay? So, one thing I want to point out is that this area is essentially, if I make this my new x-axis up here, this area is all beneath what I had originally, isn't it? Okay? And so that's going to change the way we want to add out these curves here, okay? It's going to change the way we want to think about how this system works, okay? So, if I adjust this thing, okay, so that way that this curve right here, y equals 5, is my new x-axis, what does it mean I have to do to everything? I have to do what? Subtract 5. So it'd be like taking this system right here. No, go back. Stop that. Okay? It'd be like taking this system right here and shuffling it down 5 spaces. So I would have the top boundary of this thing will be at the line y equals -5. Okay? And this would be the area I spin. This would be y equals -1 negative. Okay? And such as that. So I'm going to take that area and spin it. So first I got to figure out how do I write an integral that's going to give me this area right here. Okay? And just that area alone. Okay? What's it going to be? Okay? Isn't it going to be the entire area basically under the curve, undo, x squared minus 5? Okay? But then we're going to take that away basically from the area under y, the integral of y equals -5. Correct? Okay? So this is why things become tricky when you go on the negative side of things. Because you've got to kind of twist the way you think about things. Okay?
So we take it away, you're subtracting what?
Okay, so we essentially have our two areas in question now, because we're below the x-axis, are the stuff in the rectangle formed by the line y equals -5 from 0 to 2. I'm going to subtract from it the area bound by y equals -5 this time. Okay? And so that kind of twists things around on its end. Now, if you remember correctly, what's always the rule for when I'm doing one curve, doing the area between two curves? It's curve on top minus curve on bottom, right?
Yeah.
Okay? That's going to work just fine here. Okay? We just have to remember, since we're spinning this around the x-axis, we got to square them first. So my integral, while it seems like, this is kind of a weird setup here of what I'm doing, the integral actually works normally if you just remember that rule. When every area is on top comes first. Okay? Area on top here is still x squared minus 5. So my integral would be written as the integral from 0 to 2 of pi times x squared minus 5 squared minus, we're already done, minus 5 squared dx. And you would work that out, and that would give you the area of the volume of the system. Okay? Any questions? Becomes tricky, I know. Okay? But it should work out just fine that way. Okay? All right. Tomorrow we're going to see